All right, welcome back. A brand new section here and a new data structure to go along with it called the heap. So personally, I really like heaps, and hopefully you will too. You'll see why I like them in just a little bit. But first, back to Wikipedia. I showed this article a couple videos ago somewhere in the trees section where I was explaining that there are many groups of trees and many types of trees within those groups. We talked about binary trees mainly in the trees section. And more specifically, we talked about binary search trees. But there are many other types, and at one point I mentioned heaps. So heaps are another category of trees. So in this video, in this section, we're learning about heaps, but they are trees. So everything that applies to trees in general applies to heaps, but there are some additional special considerations or rules. There are many types within heaps: Fibonacci heaps, Leonardo heaps, a soft heap, a leftist heap. Sounds like something I might have to step over the morning after a San Francisco party, or maybe like an event at Burning Man. Anyway, there are many types of heaps. The one that we're really going to focus on is a binary heap. And actually within binary heaps, there are two different types that we're going to talk about. But first, our objectives. So we want to define what the heck a binary heap is. We want to compare and contrast min and max heaps. So those are the two types that I mentioned we're going to focus on. Then we're going to implement one of them at least, a max heap. They're very similar, and if you can implement one, you can implement the other. But we're going to focus on writing code for a max heap and add some basic methods. And then we're going to understand where heaps are used in the real world and also the data structures they help us implement, or different things that we can use them for in other data structures that we'll learn later on. So that's where we're going. Let's start with what is a binary heap. Okay, so a heap is a tree structure. It's very similar to a binary search tree, but it has different rules. So in a max binary heap, the parent nodes are always larger than the children. It doesn't matter if we're talking about the right child or the left child. It's just that the parent is larger than the children, every level down the tree. Or another way of saying that, all children are smaller than a parent in a max binary heap. The opposite's true in a min binary heap, where the parent node is always smaller than both children. So just like a binary search tree, each node can have at most 2 children. So that's where the binary part comes from. But unlike a binary search tree, there is no order to the left versus the right. So this is a max binary heap. The root is the largest node, the largest number in the tree. And to the left and to the right, again, there's no order. It's just that they are smaller than their parent. So both of these are smaller than the parent, and the same is true for both of these. 18 and 27 are smaller than 39, or 12 is smaller than 33. But there is no relationship like we had in a binary search tree. This is the exact same numbers, actually, just represented in a different way. 41, 39, 33, 18, 27, 12. Same numbers, but in a different order. This here is a binary search tree. So we have 33. To the right, we have larger numbers, 41. To the left, we have smaller numbers, like 18. To the right of 18, we have a larger number. To the left of 18, we have a smaller number. So this is a binary search tree. This is not a heap, because the rules of a heap, if we're talking about a max binary heap, every number below this number, every child below 33 should be smaller than 33. If we're talking about a min, it's the opposite. So this is the correct structure for a max binary heap using those numbers. We have the largest number, and then to the left and to the right are 2 smaller numbers. And then each one of those has a left and a right that must be smaller than the parent. Okay, so here's a couple of rules written out. Each parent has at most 2 nodes. That's where the binary part comes from. The value of each parent node is always greater in a max binary heap. That's what we're really focusing on here, but the opposite's true in a min binary heap. In a max heap, the parent is always greater than the children, but there are no guarantees between the siblings. And also, a binary heap is as compact as possible. So unlike a binary search tree where you can just keep adding on, I showed you some depressing binary search trees that were basically, they looked like a linked list. They were very one-sided. In a binary heap, it always takes up the least amount of space possible. So every left and right is filled before we move down. And also along those lines, left children are always filled out first. So we'll come back to this. Let's just quickly recap. So this is a max binary heap, largest number up top. To the left and to the right are smaller numbers. But it's important to note, these aren't necessarily the second largest numbers in the entire heap. For example, 25 and 36 are the two next largest numbers, but they are not on this same tier. It's just any number smaller on the left, any number smaller on the right. And then the same applies all the way down. So it happens that we have 36 here and 25 and 1. Both of those are smaller than the parent. Even if 25 is larger than 19, it doesn't make its way over here. And we'll talk about how this all works, but just remember, the only rule, well, aside from the fact that each node can have 2 children at most, the only real rule is a max binary heap, a child must be smaller than the parent. So again, no implied ordering between siblings. We can't figure out if, that this by default is smaller than this, or that this is larger than that, like we could in a binary search tree. There is no real relationship here, other than 2 siblings, we know they're smaller than the parent. And then also, here's a min binary heap, same idea, except we're working the opposite direction. The smallest node up top, and then both children, the only rule is that they are larger than the parent. Same thing here. But again, there is no relationship between siblings other than the fact that they are larger than their parent. All right, so lastly, why should you care about heaps? Why do you need to know this? Well, we'll come back to this once we actually learn how to implement them, because we're going to learn to implement something called a priority queue using a heap. Heaps are really commonly used to do this. That's all I'm going to say for now. If you want to research what a priority queue is, you can, but we will be implementing one using a heap in just a bit. But they are very commonly used data structure. Basically, think of a queue where we can add things in and take them out, keep track of things to do in an order, where we can also assign a priority, an importance level to each item. And it will move to the correct spot in the queue depending on its importance level. So we'll come back to that. They are commonly used. And they're also used quite a bit with something called graph traversal. So we saw how to traverse a tree. We're going to learn how to traverse a graph, which is a little more complicated, and heaps are often used to assist with that. But really, this is just a high-level overview. We're going to first learn to implement heaps, and then we'll come back to priority queues. But just know that's really the main motivation. They're used all the time for priority queues. That's why I added this. We'll come back to this. Okay, so next, we're going to learn why I like heaps, why I think they're kind of fun. There's sort of a cute little way that we can store them or represent them using a data structure that already exists. So that's coming up next.